motivation so that you can understand why I'm doing so sophisticated things. So the motivation is as follows. We consider conformal completions of space-time. So in the case that my talk will be has applications to space-time with cosmological constant. So think of asymptotically de Sitter or asymptotically anti-de Sitter space-time when we consider asymptotic completion. However, the price we pay for this completion is we have to multiply by a conformal factor which shrinks infinite space-time to some, brings infinity to some finite location in some auxiliary manifold. So if we want to work on this boundary, this is what we do. It's convenient to have some conformally invariant framework. So, of course, physicists are very talented people, and even not knowing any mathematics, they can always find out how to do such, how to do physics on this scri. But why shouldn't we see what mathematics offers and compare with this? So now the second ingredient you have to understand you have to know to understand my talk is the following. When we consider gravity, we can define fluxes, or we can define some charges or some currents, and those currents satisfy some preservation laws due to the Einstein equations. However, if we consider a theory which is conformally invariant, Einstein equations are not conformally invariant, but if we consider a theory that is conformally invariant and that consists of solutions to Bach free spacetimes, then the space of metrics satisfying Einstein equations are is a subspace of this space, and whatever structure we define on this bigger space, we can always restrict it, pull it back to the space of solutions to Einstein equations. So what I'm going to do is I'm going to define some charges and some currents which will be available here for any metric that satisfies the Bach equation, which is conformally invariant. However, due to this embedding, they are automatically valid for solution to Einstein equation. However, the advantage of those will be their manifestly conformally invariant formulation. So whenever I want, I can leave space of Einstein metrics. So whenever I want, I can rescale my metric, and still my currents and fluxes they behave covariantly or they are invariant. So this is the introduction to what I'm going to do. And this mathematically proper way of considering a conformally invariant spacetimes is through the theory of conformal Cartan connections. So a couple of my first slides are on Cartan connections, but okay, so it turns out that this Bach flat spacetimes, they can be defined as solutions to Yang-Mills equations imposed on the normal conformal Cartan connection. So our goal will be to examine the symplectic structure on the space of solutions to the Yang-Mills equations imposed on the conformal Cartan connection. And then they will apply, as I said, to solutions to Einstein equations. However, the conformal invariance of this Cartan connection will make quantities which diverge in infinity, will make them finite just by conformal invariance. So we can compare it at the end with another procedure which people call renormalization of symplectic potential. This is what people do in holography when they consider, when they extend the symplectic potential of gravitational field to the scri. So we will obtain this extension without renormalization. So let me start with Cartan connections. So Cartan connection is not a connection, although it sounds so contradictory. So consider a Lie group G, consider a subgroup of this Lie group G, and now consider a principal fiber bundle over some manifold M, such that the dimension of this bundle equals the dimension of this bigger group. However, the structure bundle is this subbundle. So this is just the principal fiber bundle, as usual. And the new element is this bigger group, which contains the structure group and which has dimension equal to the dimension of the bundle. Then Cartan connection is a G-valued one form defined on this bundle, such that contracted with the vector fields which are generated by which are generators of the action of the structure group, which are generators of these gauge transformations. So it acts as identity. So it maps the generator into corresponding element of the algebra of the structure group. And well, it behaves properly with respect to the right action of the group as usual connection. And now this third axiom which makes it Cartan connection is that actually it is not degenerate. So this is the difference between Cartan connection and the usual connection. The usual connection is degenerate and its kernel defines parallel transport. In this case, this connection is not degenerate. So it defines isomorphism between space tangent to the bundle and the
I mean, wouldn't for the usual connection, wouldn't the connection have values in H and not in G?
Yes.
But you say it's in G, not in H.
Yes, you're right. There's another difference that the usual connection would take values in the algebra of H, while this connection takes values in the algebra of G. Okay, and we define a curvature from this connection, and actually that curvature satisfies the same properties as curvature. I mean, it satisfies two main properties as the transformation law, and it's also horizontal in the sense it's annihilated by all those vector fields with general. So it's, in other words, it transforms nicely when we change section. So the easiest example is consider a bundle given just by group itself and the action of certain subgroup on this group. So this is a principal fiber bundle. And consider the Maurer-Cartan form as a connection. Then Maurer-Cartan form satisfies this definition of Cartan connection, and the curvature due to the Maurer-Cartan equation is is just 0. So this was Cartan's motivation. Let us start with this flat case and generalize our Cartan connection to something whose curvature is not 0. You can view this in this way, that we start with, that we start developing our definition in this way, that we start with the simplest example of maximal symmetry, and then we try to put here instead of 0 something which is not 0, and then we end up with this definition. There are known examples. There is affine connection. So this is this connection which, in addition to the, curvature, it encodes also the torsion of metric tensor. There is another connection, similar, which I can see this is an old version of my slides. Here I wrote Witten connection. So Witten introduced this connection in order to quantize gravity in 2+1 dimensions, and all people in particle physics call it Witten connection since then. So this is similar connection, but we make it metric. And now the idea behind, so now what will be a group and the subgroup H in case of our conformal Cartan connection? So here the idea is as follows, that consider a null cone, and our conformal geometry is a slice of this null cone. So on a given slice, there is a specific metric tensor. But if we consider a different slice, then we obtain metric tensor that is conformally equivalent. Well, if this cone behaves like cone in, say, Minkowski space. So the idea is that that given a conformal geometry, we build this null cone. We embed this null cone in 2 dimensions more bigger spacetime. So endowed with some metric tensor, which, so if our original conformal geometry has signature P and Q, we embed it in spacetime which has signature T+1, 2+1. So this big group in our construction will be group of orthogonal transformations in this bigger spacetime, and our subgroup will consist of a subgroup preserving the null direction of cone. So there are 2 approaches to this theory. One approach is, due to Cartan, is to consider abstractly to build this null cone as a space of scales at each point, given metric tensor. And there is more explicit construction due to Pfefferman-Graham, where they really construct such the two dimensions bigger ambient spacetime, and then they use the structures in this spacetime. Those 2 approaches are equivalent, but the second one is also related to the so-called tractor theory. So tractors are vectors tangent to this cone, or maybe even vectors tangent to this bigger spacetime, 2-dimension bigger spacetime, but considered at this cone, and they are subject to covariant derivatives with respect to Cartan connection or with respect to this connection of the ambient spacetime, because it is equivalent. Okay, so maybe I will skip now this precise construction, and I will give you the result that you can use. So it's mathematics. let us start here. Okay, so now consider a metric tensor, and consider a metric tensor given by some orthonormal frame, theta. And so this metric tensor defines our conformal geometry, but it will be also our solution to the Einstein equations later. So this is the space-time metric tensor. So we have the usual definitions of the metric torsion-free connection. Here we will use the Ricci tensor in Ricci scalar, but specifically we will construct from them the Scouten tensor, which looks like this. And the indices will be lowered and raised with a fixed metric, which you can consider either -1, 1, 1, or maybe some whatever you prefer to choose. At this point, this is arbitrary signature. So now, our Cartan connection pulled back to space-time takes the form of the following matrix. So here, this central block consists of the Levitch-Vita connection. So this is n by n matrix. However, we have extra rows and extra columns. So so here we put the frame with index lowered. Here the frame with index raised. And here we put the Scouten tensor. So from Scouten tensor we construct a one form by constructing one of the indices. So this is our Cartan connection corresponding to this geometry. So we can always do it. It's not a problem. You don't have to know all that mathematical introduction. However, then if you do it, then you can be surprised that this A has nice properties. So if we consider just Lorentz transformation, then quite obviously it transforms like this. However, if we consider conformal transformation, which is not so trivial anymore, then it then transforms like a Young-Mills field, and where H is maybe a little more complicated, it involves such derivatives of not only omega, but also derivatives in quadratic terms. However, we know that if some matrix valued one form behaves like this, then the curvature of this one form will have much nicer properties. And let us look at the curvature. So the curvature here has the Weyl tensor, so we can Weyl tensor into two forms. And here we have covariant derivative, exterior covariant derivative of the Scouten tensor, which has something to do with Copeland tensor. And now, upon conformal transformation, this matrix again transforms in this nice way with those corresponding matrices. So we have, in this way, we have a certain object which has nice conformal properties, if we consider. These are indices. So yeah. So this matrix. So here, this block element is a matrix, is identity matrix n by n. So A ranges from 1 to n, and B ranges from 1 to n. Here, this index denotes that actually it's not only one element, but this is a vertical vector. So A ranges from 1 to n. And here, C is contracted. Okay, thank you. Okay, so now, for instance, the Bianchi identity, which is just identity, which automatically is satisfied, it encodes some conformal identities, which we don't have to remember. If we remember all that I said, probably there are some known identities involving Weyl tensor and Scouten tensor. Okay, so now let us see what we are doing to this. What we are going to do. So now consider four-dimensional spacetime. In four-dimensional spacetime, we have one more conformally invariant structure. Namely, we have the Hodge dual that may be applied to two folds. And okay, so let us apply Hodge dual to the curvature of our Cartan connection, and let us see what is the covariant derivative. So usually this gives this is the left-hand side of the Young-Mills equation. So it's defined as follows. And if we do calculation, it turns out that there are a lot of entries here is 0, and those which are not 0, they are given just by the Bach tensor. So now this Bach tensor is defined explicitly. And as you see, this is the whole duo of those frames. So Bach tensor emerges. So if you don't remember what Bach tensor is, you can just do this operation, and then you obtain the Bach tensor. And the second lesson from this is that if normal conformal Cartan connection satisfies Young-Mills equations, then the corresponding metric tensor automatically is Bach-like. Okay, so in particular it applies to every Einstein metric. For every Einstein metric this will be 0. Okay, so if this is the case, let us now consider properly a theory of conformal, Cartan conformal connection which we put in Young-Mills Lagrangian. Let us derive the symplectic potential of this theory, the symplectic form, the nether current, and they will all be valid also for Einstein spacetimes. So this is what we did. And indeed, you have to make sure that the Euler-Lagrange equations become the Young-Mills equations, but this is exactly what happens. So if we consider variation, if we insert this our f into Young-Mills Lagrangian and do the variation, then indeed we obtain first term which produces the Young-Mills equations, and the second term which produces the symplectic potential. And if we work out in terms of explicitly what those equations amount to, here we obtain the Bach tensor times variation of frame plus this symplectic potential. So the symplectic potential is what we are interested in. And why? Because the symplectic potential is manifestly conformally invariant. So if we consider rescaled frame, and rescaled variations, then this value taken by symplectic potential is just invariant. And this is what our symplectic potential looks like explicitly. Okay, so now our first goal is to compare the symplectic potential with the potential obtained from the Einstein-Hilbert action, or maybe I should say from Palatini action. So we do it. I will not. Well, okay. This is a general part. Why do we? What do we need this framework for? So given Lagrangian, if we take variation, we obtain the equations of motion. We obtain the symplectic potential. From symplectic potential, we calculate symplectic current. This is so for two variations. We have a certain two form. A certain codimension 1 form, and this okay, it depends on in which space, but a certain codimension 1 form, and this form is closed. So when field equations are satisfied, and then we use this form to define nether current for every symmetry, and to define nether charges. And also we can define from this symplectic charges which we identify with Hamiltonian. So this is a general framework, and we want to apply this framework here. So if we forget for a moment about the conformal Cartan connection and just consider the Einstein-Hilbert action written in terms of frames, and we do this. Okay, so here is the usual standard approach. Here is our approach. Then we obtain Einstein equations. Here we obtain the Bach equations. And it turns out that this symplectic form obtained from Einstein-Hilbert action, it doesn't behave well when we approach infinity. However, this one behaves well. So let us try to compare this one to this one. And after some calculation, we find the following result. Okay, so it turns out that the symplectic potential which we calculated for our Cartan connection can be written as symplectic potential, and if we now restrict ourselves as here to solutions to Einstein equations, then it amounts to the proper symplectic potential of Einstein-Hilbert theory, however, with cosmological constant. So if you see if cosmological constant is 0, then it's not useful at all, but if it's not 0, then it is useful, you can just divide. And the difference is the symplectic potential of the topological theory of the Euler Lagrangian. Here the Euler Lagrangian was, the Euler Lagrangian is just this. So this is a boundary term we can always add. So the lesson from this is that you can, if you want, you can forget everything what I told you. And the information is that if you take Einstein-Hilbert Lagrangian and if you take it with such a topological term which doesn't change the Einstein equation, then the resulting symplectic potential is this conformal, this following from the conformal theory. And now, if we go to the now consider asymptotically the Sitter spacetime. This is so-called Graham-Pfefferman gauge, or Stravinsky gauge. Then, so the scri corresponds to rho equal to 0. And now we calculate our symplectic potential, and if we find it takes the following finite form, where G0 is the zeroth order term in this expansion, and Tij is actually well known in holography as holographic stress energy tensor, but it's just third term in the expansion. And now if we, okay, on the other hand, comparison with what people do in relativity. In relativity, people consider renormalized action, which consists of the Einstein-Hilbert action plus some boundary term, which is this part is the Brown-York, and this part is an extra part. And the role of those terms is to renormalize the resulting symplectic potential. And then they obtain this potential. So the conclusion is that our symplectic potential obtained from this manifestly conformally invariant theory is restricted to solutions to Einstein equations, is the same as the renormalized symplectic potential modulo this constant, which in case when cosmological constant is not 0, then this is not 0, so it's useful. Otherwise, if we are in flat space-time, then asymptotically flat space-time, then unfortunately this is not so useful. So I think it's a good point to stop.
Thank you very much. questions? Yes.
It's very nice. I have two questions. So, yeah, what happens if this Young-Mills curvature is actually self-dual? So then, Young-Mills equations will be implied by the Bianchi identity. I'm guessing that what will happen is that the Val tensor will have to be self-dual, but I'm not sure.
So actually, somebody already once asked me the similar question, what about self-dual? I don't remember who it was. Let us take a look at this curvature. So I think that you can, okay, so this curvature consists of the Mile tensor. So in particular, the Mile tensor will be self-dual in this case. So it means that...
But that means that the Bach tensor is identically 0.
Is Bach... yes, of course. So Bach tensor is this is solution so in that case, then Y tensor is self-dual. However, there is also this strange condition that this should be self-dual. I don't know whether this two-form wants to be self-dual or not, and whether assumptions. So this looks like some additional assumption.
Okay, so
but maybe it's identically satisfied for self-dual. I'm not sure.
I think it will be. So the second one is, what if you think so there is a local construction, but globally you have Young-Mills connection. You can look at characteristic classes and characteristic numbers. Is there, so one would anticipate that there will be a link between characteristic numbers of Chern forms of this Young-Mills connection and things like Pontryagin classes of of the Riemannian or pseudo-Riemannian geometry. You work that out?
Well, I think that this all should be known by somebody. So this stuff is not new. People know very well this Cartan connection. What is really new is this idea of using this to calculate the symplectic potential, to combining this with those symplectic methods. But going back to your question, actually, I think that the Chern class for this curvature, it will be just given by the Weyl tensor.
Square.
Oh, okay. At least for if we consider solution to Einstein equations, then this is 0, and this is just a Weyl tensor. So then we'll just obtain invariants that can be obtained from the Weyl tensor, either square of Weyl tensor or Weyl tensors times dual Weyl tensor. So we'll obtain those familiar. So for Einstein spaces, we'll obtain familiar invariants obtained from the Weyl tensor. If this is not an Einstein tensor, however, it's still Bach, then maybe this also contributes to this Chern class. So it will be something I don't know, but it's maybe worth understanding. Thank you.
Yes. So can you show this Zefferman graph on the coordinates?
Yeah.
There was such a... okay. So I want to explain this renormalization of this symplectic structure. So what is written downstairs is just the canonical one form on a slice. And you see this T plays a role of ideal momenta, canonically conjugated to this G0 map.
Absolutely.
Yes? So if you take Reuleaux constant slices and you calculate the usual ADM structure and you pass to the limit, but you have to integrate this structure over the surface. And then this normalization means that there is some problem with trace, which is total derivative, and you can remove it from the integral. And then the rest is exactly the structure you get. So this T is nothing but clever limit of ADM momentum.
Right. Right. And we provided conformally invariant approach to this
Yeah, this
clever
is
limit, yet more clever limit.
but heavy mathematics.
More questions? If not, let's start our